Alright. Do you remember where we left off? Remember, these questions are in the back of your book, so these are good to study. These will be a lot like your multiple choice questions. In fact, if you go back and look at the multiple choice, you'll find some of these questions verbatim are very similar questions. And in fact, I usually do just go through and pick one or two questions just verbatim, so you absolutely should not miss those. Remember where I left off? We did these, right? I think we did this one too. And this one? No, no? Okay. Alright, so Alice and Bill are at the top of the building. Alice throws the ball downward, Bill simply drops. Which ball has the greater acceleration after release? So after they let go of the balls, which one has the greater acceleration? Alright, just a few more seconds. I'll stop at 50. I think that's everybody. 2, 5, 8, 11, 14. Yeah. Oh boy. Okay. C is the right answer. After they let them go, or after she throws her ball down, Alice, and Bill just drops his. Now, Alice's ball will have a greater velocity, but after they release the balls, they will have the same acceleration, right? So even though her ball is going faster, it's still accelerating at the same rate, right? At that minus 10 meters per second per second. Right? We just got started. All right. So they both have the same acceleration. Which one has the greater velocity when they hit the ground? Alice's or Bill's? Alice's has the greater, because she gives it an initial acceleration when she throws it, and so it gives it an initial velocity. Or you throw a ball upward with an initial speed of 10 meters per second. If there's no air resistance, what's the speed when it returns? Throw it up, comes back down. What's the speed just before it hits your hand? More, equal, or less than 10 meters per second? Or 0. All right, just a few more seconds. Excellent. Easy, right? You drop a rock off a bridge. When the rock has fallen 4 meters, you drop a second rock. As they two continue to fall, what happens to their velocities? Stop at 40. Stop at 40. Okay, A is right. Let's go through these. You have to read these carefully. Okay, so their velocities increase at the same rate. That's just true, right? They have the same acceleration, so their velocities are going to increase at the same acceleration at the same rate. The velocity of the first rock increases faster than the velocity of the second. Okay, that's opposite what it's saying at A. It's saying that they're going to increase at different rates. But they both have the same acceleration. Okay? Now, remember the situation, I drop one rock, I wait 4 meters, and then I drop the second rock. Okay? And then here the velocity of the second rock increases faster than the velocity of the first. That's really just the opposite of B, or the inverse of B. So they're both accelerating at the same rate, so C is not the right answer. And the velocities don't stay constant, right? That they're increasing. So they both increase at the same rate. Remember, acceleration is the rate at which the velocity changes. graph of position versus time for a car is given here. What can you say about the velocity of the car over time? I'm going to stop at 50. Just a few more seconds. Okay, let's try this again. We're sort of all over the board. So here, remember this is a position versus time graph. So what about this graph tells me information about the velocity? The slope, right? So remember with graphs we have the slope and the area. We have some other things like y-intercept and stuff, but the slope of a position versus time graph gives us the velocity. So anytime I present you with a position versus time graph and ask you about the velocity, I'm really asking about the slope. What's happening to the slope here? And initially, the slope has a certain value, and then that slope changes over time. And we want to know which of these describe how that slope changes. Does the slope increase all the time? Does the slope decrease as time progresses? Does the slope stay the same at a constant velocity or constant slope? Does it increase the slope and then decrease, or can we not really say? So let's try this again. Really, I'm asking about what happens to the slope here. All right, turn to your neighbor then and ask, because we still have about a third of you that are getting the wrong answer. So turn to your neighbor and ask them what they put. All right, just a few more seconds. I'll stop at 55. Okay, that's a lot better. So it is B. Right answer is B. It slows down all the time. So here I have a big slope, and here I have a small slope. Is it positive or negative? All right, it's slope, positive slope. Tell me this. Is the acceleration, you can click in on this, is the acceleration equal to A, a positive value, B, a negative value, or is C, the acceleration 0? Is the acceleration positive, negative, or 0? Okay, remember our rules. When our velocity and our acceleration are in the same direction, what does the object do? Speed up or slow down? It speeds up. If they're in the same direction, it's speeding up. If they're in opposite directions, it does what? Slows down. All right, so turn to your neighbor and ask them what they got. Here we have something in the positive direction. It's slowing down. I'm asking what is the acceleration? All right, so a few more seconds. I'll stop at 55. Got almost all of you on board. B is the right answer. It's negative because the velocity is positive and it's slowing down. So the acceleration is opposite the velocity. Likely to have a question where I give you some scenario and I ask you to just sketch out the plots, right, and describe what happens to the velocity and acceleration. You could have that in multiple choice, but I might also give it as a free response. We'll go back over that in just a bit. All right, consider the line labeled A in this V versus T plot. This is velocity versus time. We're just asking about this line, A. what happens to the, how does the speed change with time? Not supposed to be tricky, it's just a straightforward question. Alright, a few more seconds. Alright, B is right. Look, it has a certain value. I don't know, let's say it's 2 right here, and up here it's 4. It goes from 2 to 4 meters per second. So the velocity is increasing, and the speed is increasing. It's speeding up, right? Now let's consider, is the acceleration positive, negative, or 0 for that line A? It's positive, right? Because the slope of that line is positive. Consider the line label B in the V versus T plot. How does the speed change with time for line B? Remember that with velocity, we have a magnitude and direction when we're talking about velocity in one dimension, which is what we're doing in this chapter. And the number gives the speed, and the sign gives the direction. So that's different than what we usually do, where the sign is related to the value, okay? The sign doesn't give the value, it only gives the direction. Most of you have it wrong right now. Like, most of you have the answer incorrect. In fact, only 2 of you have it right. So turn to your neighbor and try to reason out what you have. What is happening? I'm just going to draw some numbers here. I have 2, I have 0, and then I have -2. So that's what our velocity is doing. It's going from 2 meters per second to 0 meters per second to -2 meters per second. So what's happening to the speed? How does the speed change with time for this? Alright guys, look, many of you have put B. B is not right, because I'm going from 2 meters per second to 0 meters per second here. That's not an increase in speed. If anything, that's a decrease in speed, right? Slow it down. It was going 2 meters per second, and then it's not going at all. So B is not the correct answer. Alright, just a few more seconds. Looks like we're a lot better now. Okay, most of you went from B to A, but A is not right either. E is the right answer. Because if we just look at the numbers, the values for the numbers and not the signs, this object is going 2 meters per second in the positive direction, and then it comes up and it stops, it's going 0 meters per second, and then it begins to increase speed again until it's going 2 meters per second. Right, this is like our scenario where we had something that we throw up, and then it comes back down again. It decreases as it goes up, it goes to 0, and then it increases in speed. Right? Now I know what you're thinking, that here our -2 is less than 2. In fact, it's less than 0. -2 is less than 0. But when we're talking about vectors, the negative doesn't denote a value. The negative denotes a direction. Okay? So it's different than the way we normally think about numbers, because the negative is a direction and it's not associated with the value. Follow me on this? With me? This is kind of different than what we usually think about things. Alright, you toss the ball straight up in the air and catch it again. Right after it leaves your hand, before you catch it, which of the above plots represents speed versus t? Just throwing something up in the air and it comes back down again. Alright, just a few more seconds. It looks like y'all must have it right. You should write, this is the same scenario as we had in the previous one, right? So D is the right answer. I throw something up. It initially has a big speed. It goes to the top. It stops. And then it comes back down. It has a big speed, but in the negative direction. So D is right. How about this one? You drop a bouncy rubber ball. It falls and hits the floor and bounces back. Which of the following represents the D versus T graph? So I have a bouncy ball. I drop it, and it comes back up again. It's like the bounce pass up in the lab. Like just a one-dimensional bounce pass. A bounce pass to yourself. I'll stop at 55. Okay, looks like we're pretty evenly split. Y'all put B because that sort of looks like a bounce pass, doesn't it? Does it look like a bounce pass? But B is not the right answer. D is the right answer. Often your plots don't really look like the motion, right? You're thinking about different variables. And in fact, I'll show you in just a minute. We'll try to translate between position versus time and velocity versus time graphs. But here, if I drop a ball, it goes down, it bounces, and then it comes back up again. So initially, it has velocity equal to 0, right? And then down at the bottom, it has a big negative velocity. And then it has a big positive velocity. It bounces. And then up here, it has velocity equal to 0. So we want to find a graph that has that scenario. So let's just look at velocity equals 0. That gets rid of this one and this one because they have big positive velocities initially. And then down at the bottom, we have a big negative velocity. Let's see, this one's still okay, and this one's still okay because it has a big negative velocity here and here. But then it goes straight from having a big negative velocity to a big positive velocity. That's when it bounces, right? It goes from being negative, turns around, and starts going right back up again. So that gets rid of this one because that doesn't occur at this point in the graph. Whereas here, it has a big negative velocity, and then in the next instant, it has a big positive velocity. And then it begins to decrease and go back down to 0. All right. Also, one thing I want to point out about this graph here is that the slope here is the same as the slope here. What is the slope of these two lines? It should be equal to g, right, or negative 10, our acceleration. I think that's the end. Look, there's a quick test in the book, and we'll do that in just a bit. But we haven't done the Big Buck Bunny, have we? Let's do that. Sorry. We'll do that, and then we'll come back. Actually, no. Let's let me do one other thing, and then we'll do the Big Buck Bunny problems. Those are good free fall problems. So let's work on interpreting position versus time graphs. There's a screencast on the online portion of the class. Let me show you. I don't know if y'all have this. Did I send out an email about this screencast? I don't think I did. That was sent out to the other class. Yeah, I will post this. If you go to the 101 site, I have an online class, and they have screencasts for that class, and I will post this on your website. but there's a link here about plots of motion that might help you. But I'll send an email out about that today. Just if you have trouble interpreting position versus time, velocity versus time graphs, you can watch this. But we're going to do a little bit of that now. But this is just sort of a little extra practice. But I'll send an email about that later. Well, let's say that we have a position versus time graph, x versus t, that looks like this. All right? And I want to draw the velocity versus time graph that corresponds to the same motion. All right, so I want to draw a line here that describes the motion that occurs here. Right? What is the velocity initially of this position versus time graph? That is, at this point, what is the velocity? Is it positive, negative, big, small? Okay, it's very, very small. It's practically zero, and then it's positive or negative? It's positive. It's a very small positive slope. All right, so if I were to draw that on the v versus t graph, I would draw it right here. So this point right here corresponds to this point right here. And then what happens to the slope of this graph as time increases? As time goes on. It increases, right? So the slope of this graph is small here, but it gets bigger and bigger and bigger. And it's always positive. So if I were to draw a line representing this on the v versus t graph, what would it look like? It would be a straight line. Would it go up or down? It would go up, right? So my v versus t graph for this is going to look like this. This velocity versus time graph describes how the slope changes. Let's try another one. So I have an x versus t. Oh, back on this one, by the way, is the acceleration of this graph positive or negative? Positive. It's a positive acceleration. The reason we can say that, for a couple reasons. One, the slope of this graph gives the acceleration. It has a positive slope. But also we can think about this, that the velocity is positive, and I have an increasing speed. And because the speed is increasing, the velocity and the acceleration are in the same direction. So that means I have a positive acceleration. All right, how about this one? I want to draw the v versus t graph for this one. Actually, first of all, is the acceleration here positive, negative, or zero? Why don't y'all click in on this. Is the acceleration positive, negative, or zero? A few more seconds. Looks like most of you put negative. That's right. Very good. Alright, so the reason we know it's negative is because our velocity here is negative. The slope of this line is negative, so I have a negative velocity. And is it increasing or decreasing in speed? It's what? No, it's increasing. Remember when I'm talking about the speed, I'm looking at the slope. And the slope of this line is getting steeper. So I have an increasing speed. And if our speed is increasing, that means the velocity and the acceleration are in the same direction. Or as it may be. Let's see which way are you going? Same, yeah, in the negative direction, off to the left. Okay? So, it's increasing speed, negative velocity. That means I have a negative acceleration. All right, how does the v versus t graph look like this? Why don't you just go ahead and sketch it out? I'll give you all a second. Describe the velocity versus time graph. First of all, which quadrant will it be in? The first or the fourth quadrant? This is the first, this is the fourth. Which quadrant? Well, is our velocity positive or negative?
Negative.
Right, so if the velocity is negative, which is on the y-axis, that puts it in the first form. So, because this value is negative, this value is positive. So my line is going to be in this quadrant, because my velocity is always negative. Is that line going to go up or down? It's going to go down, right? Because, look, I have an initial negative yet small velocity, so that's this point, and then at the end I have a big negative velocity, so it goes in that direction, like that. So that's an increasing speed with a negative velocity. If I knew it was in the fourth quadrant, like you could take what we said over here, that is that the acceleration is negative, and this is the only line that can be, because it has to have a negative slope. You see the slope of this line is negative, it has a negative acceleration. So these are two graphs that describe the same motion. They're just position versus time, velocity versus time. What would the acceleration versus time graph look like? If I plot acceleration versus time, what would it look like for this? Okay, it does have a constant acceleration because the velocity is not changing, or excuse me, the slope of the v versus t graph is not changing. Right? Would it be in the first or the fourth quadrant? Fourth. So is that line going to go up, down, or straight? Straight. Very good. So the acceleration will look like this. All right? I said I'll probably give you all a question like that on the exam. Something along the line. I might give you a physical scenario and say, sketch the position, velocity, and acceleration graphs for this scenario. Or I might give you one of them and ask you to interpret the other two, like give you the position or velocity and ask you to sketch the other two graphs and give the signs of the acceleration and the velocity and all that jazz, okay? So y'all could do that. There are some other scenarios, but I'll leave you to practice with this. I'll send you that screencast too, that might help you as well. All right, you'll have a graphing problem. You'll have, that is where you have to interpret a graph that I give you. You'll have a function problem where I give you a function and you have to find certain things. You'll just have a straight up kinematics problem. There are several in your homework to practice for that. And then of course from chapter 1 you'll have probably an estimation problem, dimensional analysis problem. You need to know your standards, you need to know your metric system, all that business. Y'all could probably take it right now and do okay, right? I don't want to lull you into thinking that the exam will be easy because I know that some of you are not going to do well on it, unfortunately. So just from history, but I want you all to do well. I want you all to make an A. But it's probably going to be the easiest exam we have all semester. But that doesn't mean it's going to be easy. It'll just be like the exams will get harder as we go along because the material gets a little more involved. Is that a bad thing to say? It's not going to be an easy exam. Okay. All right, let's do this Big Buck Bunny problem. These are two problems, two free fall problems. Big Buck Bunny is is an open source movie. These gosh, what are they? Swedish, I think, people. They've made these movies, and they make it to sort of promote their software, but they're open source movies. But anyway, it's about this big bunny, and he's kind of a naive guy, but he's getting bullied by these three other creatures, this flying squirrel and like a hedgehog or something. And in this final scene, the Big Buck Bunny, he sort of comes off really mean, but he's sort of exacting revenge on these bullies. Right. Not that revenge is a good thing. Like, I don't want y'all to go out and take revenge on bullies. They don't have bullies in college anymore, do they? They have bullies? They have mean people. I guess those are professors. Are those the bullies in college? Okay, I'm sorry. What was I saying? So we're going to watch this clip. There are two places where we see free fall, and in both of those places, it's just something dropping, and I want you to think about what is the information that we can gather from the clip, like is it time or distance or whatever, and we'll work them in different ways, depending upon the information that we have. Back, I'm sorry, I'll start right now. What's some other things that I know? Right, So all that same stuff, acceleration is minus 10. V naught is what? Is 0 meters per second because he's initially at rest. Y naught is also 0. And like last time, I want to know what is the height that he falls. And I also want to know what is the speed at the bottom. This will be considerably easier because both of my equations, v equals v naught plus at, that each of them only has one unknown. Usually if you know your time, it's going to be a pretty simple problem. However, we can think, remember in the last problem, he was in the air for 2 seconds, or the peach was in the air for 2 seconds, and we had a final velocity equal to minus 20 meters per second, and we had a height equal to minus 20 meters. We can take these, and now we're in the air twice the amount of time, so the velocity is going to be what compared to the previous one? That is, I'm looking at this relationship right here. All right, v naught is 0, so v is equal to a times t. If I double my time, which I'm doing here, what do I do to my velocity? I double my velocity, right? So in the previous problem, I had minus 20 meters per second. In this problem, it should be minus 40 meters per second. We'll work this out in just a second, but just because I've doubled my time, I know that I should double my velocity over the previous one. All right, in the second one, if I double my time, what happens to the position, or the displacement? If I double the time, what happens? Prakash, what happened? I get a factor of 4, right? So if I double that, it's 2 times t. The 2 is squared, and then so I get a 4 over here. All right, so over here I had y equal minus 20 for the previous problem. So my answer to this one should be 4 times that, or minus 80 meters per second. All right, so we can just look at that, and you need to be able to think about how things change with variables like that. So if I double a variable, what happens to the quantity? All right, so I can figure out these pretty simply. V is equal to at. That's negative 10 meters per second squared times t, which is 4 seconds. That's negative 40 meters per second. And then y is 1/2 at squared. What was t? 4 seconds squared. So that's minus 80. All right, just like we said before. Let's do a quick test problem. This isn't a clicker problem, but on page 62, I have a graph. It's a simple graph, but there are several questions. I'll let y'all get a head start on it, and we'll finish up the class with this. The first question is, you have this v versus t graph. What distance does the particle travel between 2 and 6 seconds? Does anybody have an answer? You have it? It's 8 meters. So if I have a velocity versus time graph and I want to find the distance, I just find the area. All right, so I can find the area of this little part. That's 2 on this side, 4 on this side because it's going from 2 to 6. And so the area equals 8 meters. Now in the next part, I want you to find the acceleration at t equals 7 seconds. That's at this point right here. Go ahead and find the acceleration. They have the acceleration. Young, you have it? What is it? Negative what? 1, negative 1? That's right. Yeah, so I just find the slope of this line right here. That's my rise, which here is negative 2. That is, I'm going from 2 to 0. 0 minus 2 is negative 2. And then the run is 8 minus 6, or 2. And so the rise over the run is negative 2 over 2, which is negative 1, as Young said. So my acceleration is negative 1 meters per second squared. And then also, what is the average acceleration between t equals 0 and t equals 8 seconds? I'll leave the graph up here so you can see it. Between t equals 0 and 8 seconds, what is the average acceleration? Remember, our average is that funky thing where you do initial minus, or final minus initial velocity over our time. Oh, this should be easy. Between 0 and 8, what is my average acceleration? What you got? 0, right. So between 0 and 8, I just say my velocity here is 0 meters per second. My velocity here is 0 meters per second. So my average acceleration is VF minus VI over t. That's 0 minus 0 over 8, which is 0 meters per second squared. And then finally, what is V at t equal 5 seconds? What is it? It's just negative 2. So at t equal 5 seconds, that's right here. The velocity is equal to negative 2 meters per second. That's just because that's where that line is. All right? That's a pretty simple problem. You could see, you certainly will see interpretation of graphs like that. You'll see some more complicated ones like we've done previously in this chapter. I think that next time that we won't move on to chapter 3, that we'll spend some more time, and I want to bring you some more practice problems, kinematics problems, but we'll do some that are slightly more complicated, where we have to do substitution of one equation into another. Some of your homework questions are like this, so it would be useful if you could do your homework for chapter 2 over the weekend. Just take a look at it. You know, I recommend that you try it without looking at the solution and just see what you get, and then go back and check it with the solutions. I find that's helpful, that if you make mistakes along the way, you learn from them. All right, so and then on Monday, like I said, I'll bring in 4 or 5 practice problems. That'll be a little bit more complicated, something similar to what you'll find in your test, and we'll spend that class period working through those practice problems. Also, if you have questions about the exam on that day, we'll spend some time if you have questions about things that we've already covered. All right? Have any questions right now about sort of what to expect for next week? Or about the weekend, or today, or like? Because we have like 6 minutes. Y'all have a good day. I'll see you next week.